I got asked earlier today about a physics problem. In fact, this problem you see right in front of you on the screen. I got sent this. It's about critical angle and total internal reflection. We're talking about light traveling from one medium to another, in this case from glass into water. Let's jump straight in with part A. Two good reasons. Firstly, it's the first part of the problem, and secondly, this just involves some maths, not strictly physics as such. It's just maths, rearranging an equation and then solving for the answer. Physics problems often involve maths, and this is a prime example of how it does. If we scan down, we can actually see part C also uses the formula to calculate the critical angle. Well, that's just doing some more maths, isn't it? But we'll jump in with part A. So what we're going to do is follow a few steps. Six steps. I've actually got a video on how to solve physics calculation problems. And that video goes into this method. It's the same method I'm going to use right now. I'm going to follow my 6 steps. They would be: start with an equation. Well, this question has already given us the equation to use, so grand. Rearrange the equation if you need to. In this case, we will need to rearrange the equation. And then we put our numbers in. Step 4, we reach for our calculator, we get the answer. Step 5, we put on correct units, and step 6, we show our rounding. So let's follow those 6 steps now. Let's start with the equation. What we have is n is the refractive index, and we're talking in this case of glass. So n of glass multiplied by the sine of theta of glass. Theta is just some angle. It's a Greek symbol we use for the angle. What else are we talking about? Water. So equals, on the other side of the equation, the refractive index of water multiplied by the sine of the angle of, not a G, we want a W. Sine of the angle of water. So that's the equation that we're going to start with. The question gave us this. Grand. That is step 1. Start with the equation. Step 2, rearrange the equation if we need to. Well, we do need to. What we're actually after calculating is the angle of refraction in water. So we want this part right here, theta W. So let's rearrange that. Actually, I have another 2 videos which may prove helpful to you if you're in this sort of situation. One is on how to rearrange an equation, which I'm just about to do now. The other one is how to transpose an equation, which I'm just about to do now. 2 separate videos, but really they're about the same thing. I call it rearranging an equation. Transposing is a more mathematical term. Mathematicians transpose their formula or their equations. I just rearrange. It's really the same thing. So this is how to rearrange or transpose this equation. Let's get rid of the refractive index of W. Let's do that now. So we'll have on one side of the equation, sine of the theta of W is equal to, on the other side of the equation, refractive index of glass multiplied by sine of the theta of glass. Now, to get rid of this NW, I'm just going to take it across the other side of the equals. And when you take something across the other side of the equals, you just do the opposite. So when it was with sine theta W, it was multiplied, but now it's on the other side, so it's going to be divided by. And like I say, I have a video on how to do this, whether you want to call it rearranging an equation or transposing an equation, whether you're a mathematician or not, it's really the same thing. But I don't want sine of the theta. Actually, that's a theta, not a 0. I don't want the sine of the theta. I just want the theta by itself. So let's get rid of the sine. Well, we take the sine across the other side of the equals, and that will leave us with theta of water. Grand. What is the opposite of sine? Well, that would be inverse sine. So when we take that sine across the other side, we have sine to the minus 1, the inverse sine. And it's the inverse sine of ng sine theta g all over n of water. Right, so that is our rearranged equation. So the first 2 steps are done. Step 1, start with an equation. Step 2, rearrange as you need to. the question asked me to calculate the angle of reflection, the angle in the water. Well, that's what we have, theta in water. Step 3 is to put in the numbers. Now, I can see I'm actually running out of room. I'm not going to have room to fit this all on the one slide. So let's just go to another slide and we'll do step 3, which is put in our numbers. So we have theta of the water is equal to the inverse sine of, well, Ng, the question gives us that right at the top. The refractive index for glass is 1.5. So 1.5 times the sine of, the question gave us that as well, 23 degrees. So 1.5 by the sine of 23, and this is all divided by the refractive index of water, which is 1.3. So the question gave us all the information we need. Now we just have to solve the one unknown, the theta for water. So we've plugged in our numbers. Step 4 is get the answer. We reach for our calculator, and let me just punch this in. 1.5 times the sine of 23. That is all divided by 1.3 equals, grand. And now I'm going to take the inverse sine of that answer equals 26.8. 26.8. So that's step 4. Okay, so we had step 1, start with an equation. Step 2, rearrange the equation as you need to, or transpose it, if you will. Step 3, put the numbers in. Step 4, get the answer. My answer is 26.8. But that's not the answer. That's just a number. What we're talking about is an angle. So step 5, put the units on. Well, we're talking about an angle, so that is, of course, degrees. 26.8 degrees. But that's actually not the correct answer. The correct answer, according to my calculator, is 26.7978297. So that brings us to step 6. Show your rounding. I have actually rounded my 0.7978. I've rounded that to 1 decimal place. So I actually need to show that this answer, my 26.8 degrees, is actually the answer if rounded to 1 decimal place. There we go. To 1 decimal place, that answer is correct. And that's 1A done. Let's move on to B. In the formula, sine theta c. Okay, now this is the critical angle. So we're talking about theta c, theta crit, or the critical angle. What is actually going on here? Well, let's have a look. What are we going from? Glass into water. Let's have a barrier between the two things. Glass down the bottom, water up the top. What we have is an incident ray, a light ray, inbound from glass. It's about to go into the water. Now, this light ray is going to be refracted. What does that mean? Well, basically it means it's going to be bent. We have this imaginary line at 90 degrees to the medium interface, the barrier between the glass and the water. This line is called the normal. Now, when light is passing from a more dense medium into a less dense medium, the refracted ray is going to actually be bent away from the normal. So we have our incoming angle of incidence here is actually going to be less than our outgoing angle of refraction there. So let's just call this 1 is going to be less. Hey, where'd that go? Come back. There we go. 1 is going to be less than 2 because the light ray is going to be refracted away from the normal when it passes into a less dense medium. Conversely, if the light were passing into a more dense medium, it would be bent, it would be refracted towards the normal. But in this case, we're being refracted away from the normal. Now, the thing is, when a certain angle is reached, instead of that light ray being bent, away from the normal, but still going out into, in this case, the water, if that angle of incidence is just right, i.e. is the critical angle, then that light ray will be refracted at 90 degrees to the normal, and it will rocket that way. along the interface between the glass and the water. So we call this the critical angle. When that incident ray, the incoming ray, is just this angle, then the light will be refracted 90 degrees to the normal. Anything greater than that, any incident angle greater than the critical angle, and the light ray actually won't be refracted into the water, it will be bounced back into the glass. Now we have internal reflection, total internal reflection, for any angle greater than the critical angle. Okay, so now that we've addressed what this critical angle is, let's have a look at the formula. The formula gave us that sine of angle crit, theta crit, the critical angle, is equal to n2 over n1. So remember, n is just the refractive index, which is a way to state how much a medium will refract, will bend the light when light passes into it. It's actually given by the speed of light in a vacuum divided by the speed of light through the medium. But anyway, so we have refractive index 2 divided by refractive index 1, and the question says, will N2 be the refractive index of glass or the refractive index of water? Well, right at the start, the question told us that light is traveling from glass into water. So glass was the first thing, water was the second thing. So N2 is talking about the water, that is the refractive index of the water. So there we go, there's part B done, just a quick, no maths needed, just, hey, is N2 this one or that one? Well, it's that one. It's the refractive index of water. Grand. Part C. Use the formula to calculate the critical angle for light going from glass into water. Okay, use the formula. Grand. It gave us their formula. Remember, we're going to do our 6 steps. Number 1, start with a formula. Well, the question quite nicely gave us this. N2 over N1. Step 2, rearrange the formula if you need to. Well, I do need to because I want the critical angle, theta c. I don't want the sine of theta c. I need to get rid of that sine to leave me with just theta c. How do I get rid of the sine? I'm going to dump it on the other side of the equals, and that will of course become sine to the minus 1, the inverse sine of N2 over N1. Don't know what that extra mark is doing. Go wait, there's the N, there's the mark. Better put the N back. Grand. And close my bracket. Okay, step 3, put numbers in. So this is the inverse sine of N2. We said in the question above was the N of water, and that is 1.3. And so N1 is the N of glass, 1.5. And we reach for my calculator. Let's see, 1.3 divided by 1.5 equals, and the inverse sine of that answer equals 60.07356513. So I'm going to go with 60.1. So my answer is 60.1. Step 5, put the units on. I'm talking about an angle. My units are degrees. Step 6, show my rounding. Well, I did actually round my answer to 1 dp, 1 decimal place. So there we go. Use the formula to calculate the critical angle for light going from glass into water. That critical angle is 60.1 degrees to 1 decimal place. All right, moving on to part D. If the angle of incidence is 65 degrees, okay, well that's more than what we just calculated the critical angle will be. Will the light be reflected, refracted, or both? Explain your answer. Well, it's going to be reflected, isn't it? So remember the critical angle. We said any angle greater than that, then the light ray will be reflected. It won't pass into the next medium. It will be reflected into the same medium. It will undergo total internal reflection. Let's write that down. Total internal reflection with a little happy face. So the answer is going to be all of the light will be reflected. The question asked us, will it be reflected or refracted, or some sort of a mixture of both of them? Maybe some reflected and part of it refracted? No, it's going to be all reflected. Explain your answer. Well, the reasoning is because 65 degrees, this incident angle, the angle of incidence, is greater than the angle we just calculated, 60.1 degrees. All right, so the previous question, we calculated the critical angle for light going from glass into water, and now they've given us an angle greater than that. Well, any angle of incidence greater than the critical angle leads to total internal reflection. So because the 65 degrees that the question has stipulated, that is greater than the critical angle that we calculated in part C, then all of the light will be reflected. We have total internal reflection. Lovely. Let's move on to the last part. Why is it not possible for light to be totally internally reflected when it travels from from water into glass? Right, well, the thing about this total internal reflection, there's a caveat. This is if. The thing is, we will get total internal reflection with any angle greater than the critical angle if we are moving from a more dense medium into a less dense medium. So in the previous case, we were going from glass into water. Well, glass is more dense than water. So we got our total internal reflection. That's fine. We get that if we're moving from a more dense to a less dense medium. However, this part E has actually flipped the script. It's now saying when the light is traveling from water into glass. So we're actually going from a less dense medium into a more dense medium, and we don't get total internal reflection when that happens. Now, the reason we don't get total internal reflection when traveling from less dense to more dense, let's just have a quick sketch of that. Here is our incident ray. We're going from water to glass, so this is water, this is glass up here. And remember we had that normal, that imaginary line at 90 degrees to the boundary, to the interface. Okay, going from a less dense to a more dense medium, that light ray is going to bend towards the normal. All right, so it's going to be here. So the angle of incidence, let's call it 1, in this case is going to be greater than the angle of refraction. So you see, we're actually moving further away from total internal reflection. Total internal reflection, that angle of incidence, that ray coming in, would have to be getting closer and closer to the actual boundary. But what's actually going on is, because we're moving into a more dense medium, that angle of refraction is actually getting further away from the boundary. It's getting closer to the normal. So we're actually not going towards total internal reflection, we're actually moving away from it. So it's not possible for light to be totally internally reflected traveling from water into glass, because we only get total internal reflection moving from a more dense to a less dense medium. In this case, going from a less dense to a more dense medium, the light ray will actually be refracted away from the boundary. It will be refracted towards the normal. So there we go. Hopefully you have a handle on critical angle and total internal reflection. That's just a little bit of physics play, really. Sometimes just doing maths and sometimes just knowing some stuff about physics. So yeah, happy days.
If you like this video, punch that like button. If you want to see more videos, smash that subscribe.